Okay, last time we talked about K and N, and we tended to make these visualizations in 2D because it's easier to look at things in 2D. But in this example with two features, we have binary classification, the O class, the plus class, and for some new test point, or for any point, we're looking at the nearest training points and then looking at the labels, and we're making a decision based on that. And we talked about how there's not really any computation to do during training. And we talked about this issue of non-parametric. So we don't have some parameters that we're storing. We're just storing the training set. But I did want to say that just because something's non-parametric doesn't mean there are no hyperparameters. So in fact, we have a hyperparameter k here for k nearest neighbors. And both parametric and non-parametric methods can have hyperparameters. So training, there wasn't really anything to do, but prediction could be slow because for some point we need to compute the distances with all the training examples. So I posted some questions on Piazza over the weekend that I thought it would be interesting for you all to think about. Regarding KNN and specifically regarding these plots. Oh, I'm in presentation mode. But these plots I showed you last time with the red and blue shading and the points and all that kind of stuff, which is also available on GitHub as the demo slide. So there is a discussion on Piazza about this, and I'd encourage you to check it out. And be able to answer these types of questions. One thing I would like to talk about today is just this number 4, which is why does K and N almost always get 0 training error when K equals 1? So would anyone like to take a stab at that? Oliver?
So if you're doing k nearest neighbors with k equals 1, then that means you're finding absolute nearest neighbor. But if you're using the training set, then it actually will point to itself. So it's basically classifying itself.
Right. So to paraphrase what Oliver said, when k equals 1, you're just looking for the one closest point in the training set. And furthermore, when you're computing training error, it's like saying for each point in the training set, what is the closest point in the training set? But that'll just be itself with a distance of 0. And so for each point in the training set, you will look up itself, and then you will vote on the class, but there's k equals 1, so there's no voting. You just look at the label of that one example, which is whatever the label is that you've stored. So you're really basically just looking up the correct answer. And so you'll get a training error of 0, but like we've been talking about a whole bunch, that doesn't mean you should declare victory because we've talked about overfitting and test error and all that kind of stuff. I wrote almost for the same reason that a full depth decision tree almost always gets 0 training error, which is that if you have 2 examples with the exact same features and a different label, then you could make an error on this. Say you had 3 examples with the exact same location and 2 were of one class and 1 was of the other class. Then the minority class one, well, who knows? I guess it depends on how you break ties in your KNN code. So any questions about that? Oliver?
So in the previous slide, you talked about nearly optimal test error with infinite data. What does nearly optimal mean?
Yeah, so Oliver asked about the previous slide where I said nearly optimal test error with infinite data. So this refers to some learning theory that we're not really covering in the course, but essentially there is some sort of error that you'll never be able to avoid. So for example, if the test cases have some random noise added to them that's purely random, or once in every while the test labels just get flipped with some probability, you'll never be able to get perfect test error. Even if you understand everything about the problem, you can perfectly guess what's going to happen. If there's some purely random effects in there, you can't expect to get 0 test error on average. So there's this notion of the best possible test error you could get, the rest being kind of the additional, we can call it random part that there's nothing we can do about. And this is basically saying with very large amounts of data, KNN kind of approaches as good as you could hope to do. Okay, so just to add an application to KNN, and then we'll finish up with KNN and move on to naive Bayes. So we talked a little bit about digit recognition already in this course. And OCR, or optical character recognition, is in general this problem of turning images into characters. We like to revisit this example a lot just because it's a very classical, nice supervised learning problem, classification problem. If anyone's noticed on the GitHub organization for the course, there's a little course logo that says 340, and it's made out of these famous digits from this digit data set. So we've talked a little bit about this already, but you have an image, you have a whole bunch of pixels, and you would like to predict, in this particular case, a digit, but optical character recognition works for letters and all kinds of text. You know, you scan a whole bunch of things, and your computer knows what the text is. And so you could have, for example, 28 by 28 images and intensities for each pixel, and then you want to use those features, those pixel intensities, to predict the digit. And so if you could imagine these digits living in a two-dimensional space, I mean, they really live in a higher dimensional space depending on the number of pixels, but just as a way of visualizing what KNN is doing, you could imagine this was your training set, and you know the correct answers for all of these, and then someone gives you this new image and says, hey, can you classify this new image? The KNN way of doing this would be to look at nearby training examples, and then perhaps K is 3, so you look at these 3 that are the closest, and you say, oh, there's 2 4s and a 7, so I should predict 4. It's just another visualization of what we've already been talking about with KNN. A complication here is that it's very easy for us to just look at images of things and kind of internalize them right away, but what a computer sees is actually a bunch of pixels, and our brain is already doing a bunch of the work for us when we look at things, but a computer just sees a bunch of numbers, or actually, if we're just flattening out the images into a whole bunch of features. Yeah, some kind of strange sound. I guess we can ignore it. So actually, if we're just flattening everything out, then the computer just sees a whole bunch of pixel intensities rather than what we see. And so this makes life more complicated. So for example, to us, are these two images similar? Sure, yeah, they look extremely similar. But if you just try to use KNN and say, maybe the one on the left is in the training set and the one on the right is in the test set, and you're expecting, oh, sure, of course I'm going to find this one and use it to help decide that this is a 3, because they're so similar, the distance must be very small. But if you really just took all those pixel values and computed the Euclidean distance between them, it could be gigantic. And so what I'm visualizing here is the difference between the two images. When you take the distance, you first take the difference, and then you add up the squares. So if you shift the 3, you could imagine sort of the 3 kind of looks like this, and then you shift it a little bit and it could be completely non-overlapping so that the dark pixels of one are exactly where the light pixels are of the other. And the point of all this is to say that taking the distance between things is complicated business, right? It's not just that I take the Euclidean distance between any two things and it necessarily corresponds to human intuition of similar, because here you might have these two 3s that have a huge Euclidean distance between them, even though to us they look very similar, but maybe a 3 and an 8 that are not shifted that actually have a much smaller distance because only the 3, it doesn't look that different from the 8 actually. So this is kind of a warning about just using distance and not really worrying about it too much. And the question is, what can we do about this? And the word for the property we would like is translation invariant. We, as people, know that if I take a number and I move it, it's still the same number. In fact, if we rotate it a little bit, we can have rotational invariance and all kinds of invariants. But in this case, I'm just focusing on translation. So can we imbue our classifier with this notion of translational invariance? Because if so, then it would probably be a lot better at this classification task, in this case digits, but all sorts of classification tasks. And a very complicated way of doing this is to try to come up with a clever distance function that isn't Euclidean distance, but somehow gets at what we want, which is maybe you're warping one image into the other, and there's some score you can assign. So you could very carefully manufacture a better distance function, and sometimes that's a good idea. But probably in this case, the easier route to go is what's suggested at the bottom of the slide, which is just invent fake training data. And the way we can invent fake training data is, here's a 3. We know it's a 3. It's in our training set. Let's move it and make that a new training example. And we automatically can label it as a 3 because we'll just reuse the label. So for each training point, we can make 10 versions of it where each one is shifted a little bit. And for it to be a new training example, we need the correct answer, but we just copy over the label because it's still the same number. That's the whole point of invariance. And this has been pretty successful in practice, especially in computer vision, where we need all these kinds of invariances to actually make an effective vision system. Ali?
Yeah.
Okay.
Bayesian tells me that you need to do add a lot of transform data per image. There are so many ways that you can transform and rotate things. That seems hard.
Yeah, so Ali is saying his intuition says that you would need to add a lot of transformed images, so that's true. And then the question becomes, how well does your method scale with n? And in terms of k and n, maybe the scaling is not so appealing, at least in the basic implementation that we're talking about in this class, because maybe now prediction becomes super slow because you have this giant training set. So yes, that is something you have to balance, but that also brings up the question of human time versus machine time. So in a way, you're kind of trading human time for compute time here, in the sense that really thinking your way out of this mess might take you a month, right? But just doing this invariance thing, you could code it up in 10 minutes, and then maybe the computation takes 10 times as long, but maybe you don't care. So what you do kind of depends on where you're limited. Are you limited by human time, compute time? Is train time the problem, or predict time? Can you parallelize? All these considerations start to come into play. So I guess the short version is, this is often a good idea, but then of course there's more to it than that. Okay, that ends the KNN follow-up, and we will now start today's topic, which is naive Bayes classification. And our motivating example for this will be email filtering, spam filtering for emails. And so the question is, can we make this into a supervised learning problem? And if so, can we just throw one of our methods at it, say KNN? So the input is an email, and the output is a class, spam or not spam. And what we're going to do, and we talked about this, I think, on the second day of class, is we're going to use the bag of words feature representation, which is we're going to have a whole vocabulary of things, of words that we've seen in emails, and our features for each email is just going to be which of these words in our vocabulary was present in that email. And we talked earlier in the course about, yeah, that's kind of throwing away a lot of information because you throw away the order of the words and all kinds of other good stuff, punctuation. But it tends to work not too badly. And looking ahead to what's going to happen in the next 30 minutes of the lecture is basically we're just going to learn which words tend to correlate with spam and which words tend to correlate with not spam. And then we're going to combine that information across all the words in a new email and come up with a score telling us how much do I think it's spam, how much do I think it's not spam, and then we're going to take the larger of those two. So we're going to do that using the tools of probability, and we'll formalize this notion. Okay, so all this notation is the same as before. Xij, email I, word j tells us if something is in the email. Okay, so we won't pursue this further today, but FYI, there are fancier features for turning text into feature vectors. For example, there's this notion of n-grams, that instead of just looking at each word, you can look at each pair of words. So 2 grams or bigrams is saying each pair of words becomes a feature. You can have trigrams, etc. If you take n very large, you end up with a lot of features because there's many possible combinations of 3 words in a row. So maybe it's good, maybe it's not. You can imagine some benefits of doing that. So for example, if you're classifying movie reviews, say, so you have some movie review text and you want to classify automatically, is this a favorable review or an unfavorable review? And then you just try to learn about the word, I don't know, interesting, and is interesting going to correlate with the movie review being positive? Yeah, probably, but then you have a new review that says, oh, this was not interesting, and then everything you've learned is turned upside down. But maybe if you're using bigrams, then not interesting would be a separate column, and so you could deal with things like that. Okay, this note at the bottom is a question about storage. So you might be worried that this matrix X is going to be really giant because D might be really giant because there's a lot of words, and that's true. But each email only has not that many words. Maybe it has 30 words, even if you have 10,000 words in your vocabulary. So what this thing at the bottom is saying is that in memory, computationally, you can use a sparse matrix representation of your examples, which is just storing the indices of the words that you have. So if I have word 5 and word 10 and word a million, I can just store 5, 10, a million instead of 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, ton more zeros, and then another 1. The sparse storage format is just a lot more efficient. Okay. Review of the notation we've been using. I think you guys are probably relatively comfortable with this by now. So x26, row 2, column 6. x3 is the entire row 3, the third training example or the third email. and all that usual stuff. So before we go on, any questions or comments about this? Mohammed? Yeah.
Isn't the sparse matrix can be problematic in some cases?
Sorry, can you ask a lot louder?
Isn't the sparse matrix or the representation of sparse matrices can be problematic in some machine learning algorithm?
Can using sparse matrices be problematic in some machine learning algorithms? I wouldn't think you would get the wrong answer, but you may get things being slow. So part of it is just a memory issue. You use up a lot less memory when you have a sparse representation, but part of it is definitely a speed issue. If I only have 5 non-zeros out of 1,000,000 words, and I need to multiply or something like that, I only have to do 5 things instead of 1,000,000 things. But there may be cases where the speed up you would expect to get doesn't happen, and that could be problematic. Yeah, normally I don't use a microphone, and then when someone asks questions quietly, I don't feel bad about asking them to speak up because I'm like pretty much yelling for an hour, but now I don't have, I'm not standing on the high ground anymore because I'm using the microphone, but it's just for the filming, so otherwise I would use the full powers of my voice. Okay. So, naive Bayes is a type of probabilistic classifier that is pretty good at this spam filtering task when combined with these bag of words features. And it's based on Bayes' rule, which we put into assignment 0 intentionally because it comes up mainly in 2 lectures of the course, this lecture and then another one later on. So what is a probabilistic classifier? What we want to do essentially is, given a feature vector for an email, which we're calling xi, we would like to model the probability of seeing spam versus not spam. So p of yi given xi, that's a conditional probability. It says, condition on, given that I have this x, what do I think the probability of spam is? And that's different from what we were doing with, say, decision trees or KNN. In that case, we just had a procedure for picking the best one, but we didn't try to model probabilities. So this third bullet point may seem a bit strange to you, and we'll come back to it. It says classify as spam if the probability of spam is higher than the probability of not spam. You might think those 2 things should just add up to 1 because it's either spam and not spam, and why didn't I just write if it's greater than 0.5, then I'll classify as spam? We will come back to that, but the preview is to save us some time, we are going to end up with probabilities that are not normalized. We will not bother making them add up to 1, and we'll just see which one is bigger, and it'll make things a bit easier. Okay. So this is Bayes' rule applied to this situation. And it says the probability that a particular email is spam given its feature vector is equal to the probability that you would see such a feature vector in a spam email. That kind of makes sense. Multiplied by the overall probability of spam. So if the overall probability of spam is really big, then for a particular email, it makes sense that that thing is in the numerator, because if the overall spam probability is larger, then your estimate of a particular spam probability would be larger. That's kind of sensible. And then we have this denominator P of x, which tends to be the least intuitive of the terms in Bayes' theorem and is fortunately the one that we are going to be able to ignore for today. So these things all have names. We have the conditional probability. Well, we have two conditional probabilities. And then we have two marginal probabilities. And the one we really care about is the probability of spam given the features. OK, and right, all the stuff you see here, we have the same for not spam. OK, so I will try to graphically illustrate each of these factors in Bayes' rule. So first of all, the overall probability of spam. If the original rectangle was just all emails, some of them are spam, some of them are not. We're completely ignoring the text of the emails, but we're just saying overall, how many of them are spam. And so what we can do is we can approximate this probability, y equals spam, with the frequency that y is spam by saying number of spam divided by total number of messages. And more formally, this thing is called a maximum likelihood estimate. I mentioned there was one other lecture where we're going to get deep into this probabilistic stuff. That's the maximum likelihood lecture, which comes later in the course. But for now, it shouldn't be too hard to convince you that estimating the probability of spam with the frequency of spam is not such a crazy thing. OK, 1 down, 2 to go. The next term is this denominator term, p of xi. And it's the overall or marginal probability that we see a particular email with a particular set of features. And it's very hard to approximate this thing because there are just so many possible emails. So number of emails in our world means the size of our vocabulary, or 2 to the power of the size of our vocabulary, because for each word in our vocabulary, it could either be present or absent. So that's not actually the total number of emails, but we've decided in advance, so here are the D words that we care about, and for each of the D words, it's either in or out, so then we have 2 to the D possible emails in our slightly restricted universe, depending on D. Yeah, Bianca.
Is this what we use to normalize the data?
Is this what we use to normalize the data? This is the thing that we are ignoring, causing those two probabilities to not add up to 1 when I mentioned earlier that P of spam given x and not spam given x do not add up to 1. This is the normalizing that we're just ignoring. But intuitively, well, let me come back to it. What we want to do here is compute this score for spam and not spam. So what I'm trying to do on this slide is convince you that this denominator, this p of xi, we don't care about it. We can just ignore it. And basically, the key is this middle line right here. So we have the two scores for spam and not spam, and we just want to say which one is bigger. And they have the same denominator, so we don't actually care what that thing is. If x is bigger than y, then 100x is also bigger than 100y, and 0.25x is also bigger than 0.25y. So if we're just trying to compare different options, and they're all being divided or multiplied by some number, all that we're really saying here is we don't really need to care what that number is. We can just ignore it. So the last line here is Last line is just the exact same thing, but with the denominator removed, which is the actual comparison we're going to be performing. And really, there's two aspects to it on the last line. There's the overall term, this P spam and P not spam, which is saying if there's just way more spam, or that's not realistic, if there's just way more not spam emails, then that biases you towards picking not spam in a sense even before you read the email. And that's what those factors are doing. And then there's the part that actually involves X. So you have your kind of inherent inclination just based on what's more common. And then you have the part that's based on X, which is, oh, and I looked at the email, and this looks like a very spammy email, or it looks like a very not spammy email. And so what this Bayes rule approach is doing is it's kind of letting those two things fight it out. So maybe not spam emails are much more common, but the email looks a little bit spammy. That may make the term on the left still not bigger than the term on the right, just because this marginal probability P of not spam is so much higher. But if the email looks really spammy, then overall you may assign it to, or predict that it's spam. Any questions or comments about this? Okay, so finally we have the term, the conditional probability term P of xi given whether the email is spam or not. And this is also hard to estimate. Things involving xi are hard to estimate. But we need it. I mean, this is kind of the key thing that we need. So, so what Bayes' rule has really done for us, by the way, is taken the question we want to answer, which is we're given the email, what's the probability of spam, and kind of turned it upside down and said, given that the email is spam, what's the probability of seeing this email? So that's the thing we're trying to estimate. That's the interpretation of this conditional probability. And so you could imagine estimating this by just counting the total number of spam messages and just counting the total number of spam messages with those particular features. But that's just, you're not going to expect to have that many emails that are exactly the same, that have exactly the same feature vector. So you would be needing to estimate here 2 to the d different probabilities, because there are 2 to the d possible x vectors, and that's the real issue here, which is where we're going to bring in the naive part of naive Bayes to address that issue. Okay, so this is the big moment, and then I'll answer your question, Ian. We did the Bayes rule thing. There were 3 terms that we had to deal with. One we said we could ignore, one we said was easy to deal with, one we said is hard to deal with. That's the one we're focusing on right now. It looks kind of like this. Probability of seeing this word and this word and this word and not all these other words in a spam email. So the big assumption of naive Bayes is that we're going to assume that those probabilities are conditionally independent of each other. So what does conditional independence mean? It's very related to regular independence and probability, but after we condition on something. In this case, condition on the label being spam or not spam. So it is the equation on the board. It's saying we can approximate seeing the probabilities of seeing this word and this word and this word as the product of the probabilities, which you normally cannot do unless things are independent. And to make things are independent a bit more formal here, it's the assumption we're making is a conditional independence assumption because we're conditioning on the email being spam. Mohammed.
Yes, sir. Aren't we losing information about the sequence of words?
Okay, aren't we losing information about sequence of words? We are losing information about the sequence of words, but this is not the point where we are losing it. We lost it earlier when we decided to use bag of words as our features. Now we're losing, I wouldn't say now we're losing information, but now we are making an assumption, which is probably not true, but is hopefully okay, and we'll still get good results out of this. So we have already lost that information when we specified our features. Yeah, Ian.
So, if I wanted to mess up the spam filter, I was someone whose livelihood was based on sending spam emails. Could I send emails that didn't look like spam? Wrong numbers, but like wrong emails. Like, hey, is this?
So Ian is asking how he can cheat the spam filter using this information. I suppose if the spam filter was doing this kind of thing, then the best way to cheat the spam filter would be to avoid words that tended to appear in spam emails.
But what if you train this? What if you train the spam filter to accept a very low degree of words by sending like false emails like that didn't seem like spam?
I see. Okay, so I think Ian is saying he wants to hack this or cheat the spam filter by influencing the training. Okay, so that is a complicated one. The thing is, it is true that every time you flag an email as spam, say on Gmail, they can improve their spam filter, not just for you, but for everyone, because they have one more training example of an email and the fact that it's not spam. I think probably what they do, at least for the important messages, it's some combination of your personal training examples and the overall training examples. To what extent you could influence the spam filter by sending yourself messages that were spam but not flagging them is probably very small. Yes. Miriam.
So this assumption means that if you want to use string base for every application, first of all, you should make sure that first or condition will be.
Yeah, Miriam is basically asking, I think, if we want to use naive Bayes, do we need to make sure that this is true for our features? And I guess not really. If you want everything to be correct, sure, you would like this assumption to hold, but you can still get a useful classifier. It's kind of like the IID assumption that we talked about before in terms of training and testing. It brought us a useful framework, and then we would probably violate it every time. But it was okay, and I guess it is useful to understand what your assumptions are, but it is also useful to violate them to some extent. Forget your name.
Kyle,
Kyle.
would this tend to over or underestimate the true probability?
Would this tend to over or underestimate the true probability? Yeah, I need to think about that. I think overestimate. So if you take a joint probability of two variables and they're independent, then actually I don't know. Let me answer that later. Yeah. Okay. Name?
Edwin.
Edwin, right.
So because of the right side does the multiplication, so the more words I have, the smaller the probability is?
Right. Okay, so Edwin is asking, you're multiplying a whole lot of things, and so the more words I have, the more probabilities I'm multiplying, and so I'm going to get smaller and smaller numbers. So there's two answers to that. One is that it's true, but you're doing that same thing for spam and for not spam. In both cases, you're multiplying a ton of small numbers. And so, yes, you may get two very tiny numbers that you're comparing, but it's kind of a fair situation. But the other point is that from a numerical point of view, and this is either in the slides or the bonus slides, you typically take the log of each thing so that instead of multiplying a ton of really, really tiny numbers, you're adding the logs, and then you are in better shape numerically.
But if I have two emails that are both spam, for example, the first email contains words ABC, second email contains word A, B, C, D, E, F, G.
I see, yes. So, right, there's a problem with the way this is presented, which is that you have all the words in your vocabulary. So say there's a fourth word like, I don't know, dollars, and that was not in the email, you would have times the probability of not having dollars in the email given spam. So it's not the case that you're just taking a product over how many words there are in the email. You're taking a product over D things, probability of this, probability of not this, probability of this, and so it's the same regardless. Yeah, the slide could be improved to reflect that. Ali.
Would there be an issue if, let's say, the probability of something is 0, and then that just cancels?
Yeah, great. Ali said, is there an issue that your estimated probability is 0 and that just obliterates the whole multiplication? That is a problem which we will address in the remaining 17 minutes. Okay.
7 minutes left.
Oh, 7. Oh, wow. Okay. Okay, well, that's good to know. Glad we brought it up. Okay, so let's proceed at a faster rate. We need to estimate each of these things that we're multiplying together. And we're going to estimate them, again, just by counting. But now there's not 2 to the D things we need to worry about because we're just estimating for each word separately. We take, for example, the spam messages. We have a particular word, Vicodin, and we just say how many of these emails contain the word versus the total number of emails, and then we've estimated the probability. So for each word, it's just the frequency of that word occurring within spam emails. That's our estimated probability. And then we're good. So given the time limitation, this is just a more general formalized version of what we've already saw. We ignored the denominator. Then to get to Edwin's point, we're multiplying D things every time. So for all the words, we multiply those probabilities of either presence or absence in an email. And then we have the overall E of Y. Okay, getting to Ali's point. So if you have a particular word and you haven't seen it in any spam email in the training set, then you're going to estimate that frequency is 0 because it was number of spam emails with that word divided by number of spam emails. And so now, just because of this one word not appearing in any spam email in the training set, you've estimated that, oh, I could never see that word in a spam email. Probability 0. Because since I've never seen it happen, I don't believe it could ever happen. But that's not quite right, because your training set is limited and you haven't seen everything just in your training set. And so you're going to be multiplying all these probabilities, and one of them could be 0 because you've never seen that word in a spam email. And as Ali pointed out, the whole big multiplication of stuff is 0 just because of that one word, which doesn't make sense. It shouldn't be the case that just the presence or absence of one word makes you 100% sure that this is spam and you completely ignore everything else in the email, right? Which is what I'm describing. So the problem is solved with something that has a fancy name, Laplace smoothing, but what it really means is that you pretend that you've seen it all once. So every time you count anything, count number of spam emails total, count number of spam emails with this word, count number of not spam emails with that word. Every time you're counting anything, you just add 1 to that count. And it's kind of a hack in a sense, but it means that if something never occurred, it'll be as if you've seen it one time, and it will not completely derail your computation, because instead of saying I've seen this 0 out of 1,000 times, you'll say 1 out of 1,001. That's still pretty close to 0, right? So it's not messing things up too badly, but it avoids this problem of just obliterating the entire calculation with a 0 multiplied by a bunch of potentially meaningful numbers. So that's this. And you can also add some number other than 1. So you can add a number beta, and just by adding 1, you've basically already solved the problem. But by adding more than 1, it's called smoothing, because you're sort of smoothing out your data set. And if you made beta some ridiculously large number, then all your actual training data would become insignificant, and you would just predict a half probability for everything, which is like the most smooth case. So it's kind of a slider between trusting your data ridiculously much and even believing that something's impossible just because you haven't seen it once, which doesn't make sense, to not trusting your data at all and completely ignoring it, which doesn't make sense, to this slider beta that takes you between those two extremes. Okay. 2 minutes left, so I'll probably have to talk about this more next time. Sorry, I don't have time for the question. But I'll just quickly say that you may also care differently about different types of mistakes. So if you let in a spam email into my inbox, I'm not going to be that mad. I'll just delete it. But if a very useful, important, regular email gets put into spam and I don't see it for 2 weeks or ever, I'm going to be really mad. And so your penalty or loss or cost or whatever you want to call it for the different types of errors, you may want that to be different. And so for those of you who haven't heard of these words, if spam is considered the positive class and not spam is the negative, we have words like false positive, which means you said it was a positive, but it actually wasn't, or true negative, which means you said it was a negative and that's true. And you can use decision theory to assign a score of unhappiness to those different cases. So I have no unhappiness on the diagonal because I'm correct. But I have 10 level of unhappiness when I let a spam email into my inbox, and 100 unhappiness when I missed a spam email. And you can actually train your system to be optimal with respect to these costs. So minimize the average amount of unhappiness I'm going to invoke when I run my filter, which is going to bias you, in this case, towards predicting not spam, because it's just too painful to predict things as spam and have to pay this cost of 100. So I don't have time now for this example, and I'll probably need to go through this next class. But let me just do the summary and then we can finish. So comparing naive Bayes to decision trees, which we've already talked about. With naive Bayes, we're using all the features at once. We're not just looking at them one at a time. And we have a conditional independence assumption that may or may not be perfect. Just like with decision trees, our greedy algorithm may not be perfect. It's easy to update this naive Bayes when you get new data because you're just incrementing a couple of counts. And with decision trees, you might have to make a whole new tree. And this tends to work pretty well when your assumptions are more or less correct, which is often the case with text. So that is it for today. I will go through these last few slides next class, and see you then.